Hi, my name is Nazarii Romankiv, and today I will be presenting you the results of our article AI Agent for Conversational Q&A over SaaS codebase using large language models. So let's start with the introduction, why and what we did. So the SaaS is now the dominant software delivery model powering critical digital infrastructure across every industry. The cloud-native SaaS codebase are huge and complex. It's millions of lines and dozens of microservices and multiple repositories. Developers spend excessive time just finding the answers. Legacy code, scattered docs, and keyword search slow both veterans and new hires. Traditional search and static docs can keep the pace with agile release cycles and rapid architectural changes. At the same time, LLMs enable conversational understanding of the code, turning natural language questions into precise, context-aware answers. We did some analysis of related works and of what people did similar in the industry with LLMs and how they experimented. So first of all, we have found out that some people have experimented to use LLMs for code generation accelerators, where students and teams lean on Copilot and ChatGPT for scaffolding and boilerplate tasks, but effectiveness hinges on manual prompt crafting. We also found out that some people use LLM-driven code analysis, where they write sophisticated prompts and let the model rival static analyzers for vulnerability detection and config file repair. But runtime cost and false positives, they sort of limit at scale. At the same time, prompt engineering frameworks like workflow platforms and LangChain, they standardize role setting, memory chain, and retrieval, cutting the time to prototype LLM apps. Few shot prompting and project-specific adaptation. Essentially, with few shot prompting, there is work that shows that it surpasses fine-tuning for code summarization, and especially if you add a static analysis on top of that, it really boosts the quality further. And there also was an attempt to build in IDEA conversational helpers tools like Guild. They sort of embedded selected code in GPT queries, giving on-demand explanations that lift task success for professionals, yet they still rely on ad hoc snippets rather than whole code-based reasoning. If you talk about limitation across all the studies, they focus on isolated files and snippets, not multi-level SaaS systems. The interaction pattern is prompt response, there is no persistent memory. The code retrieval and draft reversers are external to LLM. Developers must supply the right snippets, and evaluation centers on generation quality, not on end-to-end developer productivity and large-scale maintenance. So the goal of this article is essentially to build an end-to-end AI agent for natural language Q&A over large evolving SaaS code bases. Concretely, the agent should index the code base, accept plain language questions, and return precise cited answers or navigable code paths, maintain conversational memory, allowing to follow up, and support onboarding, debugging, and architectural explanation, cutting search and call time and accelerating future delivery. So, as for method and materials, I have prepared for you the following table. It essentially explains each layer and what we use on every of them. Let's dive deeper into that. As for language, we use Python because it's de facto the standard language for AI and NLP. Right? It has rich ecosystem, it's fast for prototyping, it's beautifully perfect for our use case. As for API of our server, we're using Fast API because it's natively asynchronous API. It's really built for high throughput, which matches with the goal of this article. As for agent framework, we have selected LangChain, again de facto the standard of that enables us to build faster and scalable AI agents. As for message broker, we have selected RabbitMQ. It's allow us to build reliable queues and handles back pressure when we need to process hundreds and hundreds of files for indexing into our open search. Right? Open search is essentially we use it as a vector storage because of its proven record of success for scalability, right? And it also has out-of-the-box support for vector search. As for primary database, we have selected MongoDB for its flexible schema. And for LLMs, essentially we use Cloud 3.5 Haiku and Cloud 3.7 Sonnet. We have selected these models because they excel at code understanding, and we use both of them in different places taking into consideration speed with reasoning trade-off for each stage. Like for example, we use smaller model haiku for summaries and key entities instruction, and we use model sonnet for chat, where we need a more comprehensive understanding of the context and for the model to be able to drive the discussion. At the same time, we have selected embedding model from ChatGPT, OpenAI. It's text embedding 3 large, but we have downscaled its dimension from 3000 to 1000. We did this to improve scalability of our system, because the vector size is really important for us, because we will be indexing thousands of files, and essentially reducing the vector size helps us make the system more scalable. At the same time, there is a little decrease in the quality of semantic search. As for evaluation codebase that we were using to test our agent and our prototype, we were using open source burn-stacked ERP system. Essentially, it's a realistic SaaS application, and it has a business complexity in it, right? Because it's an ERP system. Was for experiment, our AI agent consists from 2 parts. The first part is a content ingestion pipeline. At this stage, essentially, we read each file content from the source code, and we add it to a processing queue. Essentially, it's a Rabbiting queue where we do it to ensure that our AI agent pipeline for ingestion is really scalable, as we will need to process hundreds of files in the end game if we use it with realistic SaaS code base. Then we have 2 steps. We first generate a summary with prompt engineering. At this stage, we use haiku model, and we also at the same time extract key domain entities mentioned in the code, so that we could later use it as a metadata for vector embeddings. Then we append the summary as a documentation comments to the file, and we generate embedding. In that way, we improve the recall and precision for search, right? And the final stage, we index the file embedding with metadata, where we include the file source, the key entities, etc. This enables us to do a hybrid search when we sort of search by key entities plus semantic search with embeddings, right? Then the next step is the second part of our agent is essentially end-to-end integration of AI and backend with AI agent infrastructure. So we have a React-based user interface. The user can ask the question. The React-based user interface keeps a webhook with our fast API server, where we host our AI agent, and we use MongoDB to store message history and agent state, and we perform vector search when the user asks the question. The agent search for relevant source code in our open search index, and at the same time, when we have all the necessary context, we use Cloud LLM API to prompt with relevant context and message history and get the response for the user. And the last part that I want to highlight of our prototype is cognitive architecture of AI agent. Essentially, LLM, it's a very broad tool. So we built a cognitive architecture to guide it through the right steps of thinking and the right prompts, right? So essentially, each step is a separate prompt engineered system prompt to our LLM to achieve a certain step. In our case, we first revise the user question to be optimized for the search, because the user can ask anything while they're in the context, but we need to generate a full query that's better suited for search, taking into consideration the context of the chat where the user asks for it. Then we search for relevant code fragments using open search. At the end, we assess the relevancy of the found fragments. Again, here we use LLM prompt engineering, and if fragments are relevant, we sort of generate the answer. If no, we start from the beginning and try to find again, rewrite the query, search for the documents, assess the relevancy. Then let's talk about the results. So if we assess each part of our architecture, so first is ingestion pipeline metrics per 100 files. You can see that the processing time is almost 1000 seconds per 100 files. The cost of embedding is really cheap. It costs less than 1 cent to embed 100 files. At the same time, we have a relatively higher cost of summarization. It's 4 cents to summarize 100 files and 13 cents for extraction of entities of 100 files. It's actually for taking into consideration how much money huge SaaS systems spend on engineering, on hosting. It's actually really cheap and affordable for any SaaS application developers. Then we have built agent interaction UI. This is just a brief screenshot of how it looks like, and you can also see the example of answer it generated for the user question. It's really simple, minimalistic. It does its job for testing of our prototype. And then there is some metrics for agent interaction. So average response time, it's 28 seconds. It takes time to rewrite the queries and find the relevant search documents, but it's still very, very much faster than if you would try to spend that time finding these documents and files in the original code bases and the original documentation or asking your colleagues. So it's really, really time efficient considering comparing it to the communication with real people and search of the documents. And it's really cheap. It's really like the average cost of one answer is $0.004, right? So it's super fast and it's super cheap. As for the discussions, so the key benefits of what we did, the presented AI agent for conversational Q&A over SaaS code bases, it really demonstrates tangible benefits in addressing one of the core difficulties in modern cloud-native software engineering. It's essentially efficient knowledge retrieval and onboarding. We combined LLMs with vector-based semantic search, and therefore our system delivers contextually relevant information to developers in intuitive dialogue format, and significantly reduces the time spent on manual code exploration. At the same time, one of the direct advantages of this approach is rapid onboarding of new engineers, because traditional knowledge transfer is often slowed by outdated documentation and scattered institutional knowledge. But our AI agent alleviates these bottlenecks by maintaining updated semantic indexes via OpenSearch. And this aligns with insights from one of the related works that we found out that how context-aware assistants integrated into developer workflows reduce the friction in comprehending unfamiliar code sections. As for important consideration of what we found out from doing this AI agents, that our ingestion pipeline really incurs time and cost. Also, this is acceptable for moderately sized repositories. This pipeline needs to be parallelized and perhaps distributed across multiple workers to handle massive enterprise scale code bases rapidly. There is still a potential for hallucinations, like other LLM-centric systems. The AI agent might generate confident yet inaccurate responses, this issue known as hallucination, while we mitigate this risk via retrieval augmented prompting. But users must remain vigilant and confirm super critical information. For majority of it works perfectly fine. As for scalability of vector indexing, OpenSearch natively supports high volume indexing. Maintaining real-time code-based coverage in dynamic SaaS project can become computationally intensive. So large refactoring or frequent incremental updates might necessitate micro-batch ingestion or near continuous indexing. Future work will explore incremental embedding strategies that minimize reindexing time when only like a certain file changes. As for the quality of summaries and entity extractions, also Cloud 3.5 Haiku models provide fast and coherent summaries. There is no guarantee of perfect accuracy for especially intricate modules or unconventional code structures, ensuring robust domain adaptation. Potentially, this can be mitigated with local few-shot examples, but this remains as a key step to improve summarization consistency. As for security and privacy implications, embedding sensitive code and shipping it to external element points raises confidentiality concerns, especially for enterprises. Self-hosted or on-premises LLM deployments could mitigate data exposure risk, but introduce new complexities in model management and hardware costs. As for conclusions, so the summary of our article is the following: that we had a challenge. The challenge is to scale SaaS teams. It demands faster onboarding and instant access to up-to-date code knowledge. The solution is a two-part AI agent. We have built a scalable ingestion pipeline that indexes code bases, and we have built a UI where developers can ask in a natural language questions and receive cited code answers. The core stage that we used is Cloud 3.5 Haiku and 3.7 Sonnet models, OpenSearch vector storage, MongoDB database, fast API, and LangChain backend. As an outcome, the prototype shows seamless dialogue-based retrieval of relevant code fragments and explanation, cutting exploration time for complex SaaS projects. As for future improvements, there is quite a huge list that we can do to make it even better and solve more problems for big teams developing SaaS systems. First of all, is auto reindex via VCS hooks. So you need to integrate it with GitHub and GitLab webhooks to embed changes on every push. It also needs better support for multi-repository, right? So you need to unify ingestion across multiple services and languages in a single knowledge graph. At the same time, toolchain fusion, right? This tool could benefit significantly if we were to connect it with Jira, with Confluence, CI logs, etc., to enrich the answers with design intent and issue history and the documentation from Confluence, rather than just looking in the codebase. We also need to, as one of the points for improvements is continuous evaluation loop. We could add a step to capture users' feedback to then fine-tune the prompts, embeddings, and ranking quality. And last but not least, we need to explore enterprise deployment options and explore on-premises LLM hosting for intellectual property protection and lower generation cost at scale, right? And last but not least, there is deeper reasoning capabilities, like we could investigate adding a static analysis signals and chain of source prompting to reduce hallucination and boost explanation accuracy. Really huge potential on this topic, and it requires there is more work to do and more researches we can do in the future to improve this agent even further and solve more problems for teams that build huge systems. So that's it. Thank you for your time.